Hello everyone, welcome to my videos on elementary differential equations. This is video number 18 for chapter 2. Okay, let's get started. The topic for this video are the exact equations. Before we start on that, let's do a little bit review on partial derivatives and chain rules for functions of two variables. Consider now a function, let's call it f, and it depends on two variables x and y. And then we can define the partial derivatives of f with respect to each variables. So we will use this notation f sub x to denote the partial derivative of f with respect to x. And similarly, f sub y will be the partial derivative of f with respect to y. And furthermore, one can define higher order derivatives by simply putting more of the x or y in the subscription. So if we write f sub xx, that means we differentiate f with respect to x twice. And then f sub yy will be the second derivative, partial derivative of f with respect to y. And similarly, one can use the same notation to define the cross derivatives. So if we write f sub xy, that means I will take the function f, take partial derivative with respect to x, and then take the partial derivative with respect to y. So in particular, this means the following. You will compute this partial derivative first with respect to x, and then treat this as a function, and then take partial derivative with respect to y. Okay? And if you shall exchange the order of that partial derivative, then it's f sub yx. It can be written in this form, and it means that you differentiate f in y first, and then take this function and do the partial derivative in x. Okay, so if the function f is smooth enough and can be differentiated twice, and then we will have the identity f sub xy would equal to f sub yx. So switching the order of the partial derivative does not change the outcome. Now let's look at the chain rule. We now consider x a function of t and y a function of t. And then we form a composite function as f originally is a function of x and y, and then now x depends on t and y depends on t. Then we can write like this, and then we see that f actually depends only on x. Okay, so we can use the chain rule to find out the derivative of f in t. So df dt, what would that be? You apply the chain rule, you do the partial derivative with respect to the first one, so partial f partial x, and then you differentiate x in t, so dx dt. And then you go on to the second chain, differentiate f in y, so partial f partial y, times and differentiate y in t, so dy dt. Okay, and we can also write it, use the shorthand notation we introduced. So this one is just f sub x, and this one will be x prime, because x is a function of t now. That's the notation for the derivative. And plus, and this is f sub y, and this is y prime of t. Okay, and let's take an example of this chain rule and the partial derivatives. Okay, so let's consider f of xy is x squared y squared plus e to the x. And then let x and y be functions of t. So x of t is t squared, y of t is e to the t. And then now we consider the composite function f of x of t and y of t. And we wish to compute the derivative df dt. So recall that formula on the previous page. We see that we need to compute lots of derivatives before we can put them together. So we need to compute f sub x. So how do you differentiate function f of x and y only in x? Well, you would only treat x as a variable, and y will be treated as a constant here. Okay, so differentiating this term in x, so you are just differentiating a constant times x squared, which give you 2x times that constant, which here is this y squared. Okay, and the second term you differentiate it in x, and you get e of x. Okay, once that's understood, then we can try our hands to do the partial derivative in y. So here in this function, if I differentiate in y, then all the terms involving x are treated as constant. So this is treated as a constant, and this is treated as a constant. And let's differentiate. So a constant times y squared, differentiating y, will be 2y times that constant. So it's 2y times that constant. And then this is just a constant. You differentiate in y, it's 0, so it doesn't contribute. Okay, and then we also see that we need x prime and y prime of t, so which is simple. So x prime gives me 2t, and y prime is e to the t. Okay, now we can use that chain rule formula and do the computation. df dt would equal to fx times x prime of t, so fx, this is the term here, and x prime of t is that term, plus f sub y, which we put here, and y prime of t, which we put here. So you can just put those in and immediately get this expression. And then it is often desirable, since we now treat f as a function of t, we can plug in the expression of x and y as a function of t. So if we do that, then we get 2t times 2, x is t squared, y squared is e to the 2t because of that, and then e to the x is e to the t squared. Okay, so wherever you have x, you put it in t squared, so get t to the power 4, and then y, you put it in e to the t and e to the t. Okay, so in the end, we have a function only depending on t. Now, there is a special case of interest in the study we were doing here. That is, if now y is a function of x, and then that function f, which is a function of x and y, we now form the composite function of f of x and then y of x. So this in the end becomes a function of x. Okay, and then we can compute the derivative, use chain rule for this one. So df of dx would be f partial derivative in the first one in x, and then x dx dx. And then the second one, df dy, differentiating in terms of the second one, and dy dx. Okay, and then we know dx dx is just 1, and this is y prime, and let's write the shorthand. It's fx plus f sub y, y prime. Okay, so try to remember this form, which will be very useful. Okay, so now let's begin talking about exact equations. Let's take an example. Let's see. Let's say y as a function of x is the unknown, And we have this equation. Let's look at it. 6x plus e to the x y squared plus 2e to the x y prime equals 0. Okay, so we first see that it's a first order equation, but it's not linear. These are not linear terms. And we tried to separate it, and then we see that it's not easily separable. So none of the method we know can really be easily adapted to solve it. And however, there is a magic function. So let's define the function psi, depending on x and y, function two variables. And then we define it to be 3x squared plus e to the x y squared. Okay, so y, well, this will come later. We'll just say this function is important for this problem, and you will see why. Okay, and then let's compute the partial derivative. Psi sub x, if we do that, we get 3 times 2x, which is 6x. And then here we'll just get ex y squared, which is here. And then phi sub y, differentiate this in y. This term is constant, nothing. Here we get constant times y squared, so 2y times that, which is this one. Now you're already seeing why I put that function up. And in fact, we observe that this here is exactly phi sub x, and this term here is exactly phi sub y, right? So this equation here can be written as this one, phi sub x plus phi sub y prime equals 0. Okay, so now comes the chain rule, the special form of the chain rule we just talked about. So this expression on the left-hand side, if you don't call this psi, you call this f, you notice that is the chain rule. Okay, so let's consider a function psi of x of y of x, and then we do the derivative d psi dx. We will get psi x plus psi y prime, and which is exactly the left hand side of this equation, so it's equals 0. So we basically know that d psi over dx is 0 for the psi function we defined here. Okay, so if the derivative of this function is 0, then this function must be a constant, where this constant c here is arbitrary and could be determined by eventually the initial condition. Okay, and then we see that we have found the solution in an implicit form. So let's put in the function psi here, that's the psi, and the equals to constant c. So this is a relation must be satisfied by y as a function of x if it's a solution to the problem. And then in this example, this is a rather simple kind of implicit form. We can try to move everything with x to the right hand side and write it out in an explicit way. So we can move this term to the right and then divide both sides by e to the x. So we get y squared is e to the negative x times bracket c minus 3x squared. And then we can take the square root and write out y as a function of x with a plus and minus sign. Okay, so here the constant c and the sign here, plus or minus, should be eventually determined by initial condition. Okay, so now let's generalize that example and pull it up to an abstract level. So let's give the definition of an exact equation. So an equation in this form, some function m of xy plus some function n of xy, y prime equals 0, is called exact if there exists a function psi such that psi sub x equals m and psi sub y equal n. So this will be psi sub x and this is psi sub y. And then we know from the discussion of the example that psi equal to constant will be a solution. Okay, let's ask some questions. So first question, how do we check if an equation is exact? Well, we can use the identity psi xy equal to psi yx. Okay, if this identity must hold, then we see that since psi of x is m, then the left-hand side here is m sub y, and psi of y is n, then the right-hand side is n sub x. Then we must have this identity, m partial derivative in y equal to n partial derivative in x, which can be easily verified because these two are given functions. Okay, so once we perform this test and find out the solution is an exact solution, so how do we solve it? Well, the answer to that question is that then we need to find this function psi. And once we find it, then we get an implicit solution, psi of x and y equal to c, an arbitrary constant. Finally, the big question here. Now, how do we find the function psi? The answer is the following. Okay, and then we will use the two facts, that is psi x equal m, and then psi y equals n. And then we'll try to integrate. We'll integrate this in x, and integrate this in y in some way to find this function. And the details will be reviewed through examples. Okay, so the next example is a simple one. We just want to check if the equation is exact. And the equation is given here. Okay, so we see that this is our function m, and this is our function n. And then we need to check the partial derivatives. So m sub y, differentiating this in y, I'll just get this term, which gives me 3. And n sub x will only get contribution from this term, which is 1. And we see that 3 does not equal to 1, so this is an inequality, so it failed the test. Therefore, the equation is not exact. Okay, let's put some remarks. Let's consider a separable equation, y prime equal f prime x g of y. Then we can multiply both sides by g of y and rearrange terms. So g of y goes over here, and then we can put this to the right hand side with a negative sign, and we set that to be 0. So we get this equation. Now let's check if this is exact, which is quite clear, because if you differentiate this m function, which now is f, in y, well, it's only a function of x, so it's 0. And you differentiate this in x, which is only a function of y, is 0. So it's an exact equation. So based on this discussion, we may conclude that all separable equations can be rewritten into an exact equation. But however, the exactness of an equation is up to manipulation. That's what I commented here. So consider the same separable equation in the previous remark. And if we now rewrite it in a different way, that is, we simply move this to the other side of the equation. So we'll have this minus y prime equals 0. Okay, and let's check if this can be exact. So m now is this fraction expression, and the function n is just here. Okay, -1, but doesn't matter, it's a constant. And then we know the partial derivative n sub x is always 0, and then m sub y is this function differentiating in y. In general, it's not 0 because it's a function of y in general. So the equation this way written is not exact in general. Okay, so here I just want you to be careful. So if you say an equation is exact, one needs to specify in which form you present your equation. Okay, so the separable equation presented like this is not exact, but if it's presented as in the previous one, that is multiply by g of y, put it in front of here, and that is an exact equation. Okay, so just want you to be careful here. Okay, so that's all I want to say for this video, and the next video we will look at a couple more examples, and in particular how to find the function psi and in various cases and some tricks of solving it. Okay, hope you enjoyed this video, and I see you next time.